Today we're going to discuss incredibly massive black holes, and specifically a confirmation that we've discussed approximately 6 months ago of one of the most massive black holes ever discovered, and in this case found completely by accident inside an extremely famous image. The image of the Einstein lens you see right here, referred to as the cosmic horseshoe, representing one of the most famous Einstein lenses ever detected. And turns out this image was hiding something absolutely incredible. At approximately 5 billion light years away from us, in a galaxy known as SDSS J1148 plus 1930, a few months back researchers officially discovered what seemed to be a supermassive black hole with a mass of 30.6.3 billion solar masses, or nearly 8,500 times more massive than the central black hole inside the Milky Way.
Well now, that's staggering 8,500 times our Milky Way's Sagittarius A*. It's remarkable to think of a black hole brushing up against what we consider the theoretical ceiling. Nature seems to delight in pushing past human-imposed limits.
But the reason this was so bizarre is of course because this is technically considered to be almost at the practical limit of how large black holes should be able to get. And so let's discuss this discovery in a bit more detail, compare this to some of the other discoveries known to us, and talk about why this is important. But I guess first let's talk about the study that you can find in the description. And so here in a recently published and peer-reviewed study by Carlos Melo Carneiro and the team you see right here, scientists officially confirmed that this is an ultramassive black hole, and moreover amongst the top 10 ultramassive black holes ever discovered anywhere. And right now scientists emphasize that there's actually a bit of a probability that it might be even more massive, potentially the most massive ever seen. But what exactly makes this classification so unusual, and what's the difference between this and a supermassive black hole?
Curious, isn't it? The distinction between supermassive and ultramassive feels almost semantic, yet it reveals so much about galactic evolution. Anchors of galaxies indeed. Without them, the grand spirals and ellipticals we admire would likely unravel.
Well, usually supermassive black holes like Sagittarius A* in the center of our own galaxy have to have a mass of at least 1 million solar masses, and we expect them to exist at the heart of nearly every galaxy, with some minor exceptions. They essentially usually act as a kind of a gravitational anchor around which the galaxy revolves. And while theoretically there is really no limit for how massive black holes could become, practically, there is a limit just based on the age of the universe. Since today it's assumed that the universe is about 13.8 billion years old, and since we know there's actually a limit to how fast typical black holes can grow in size, there is obviously a limit to how big they should get. And this limit actually exists because of the very simple physical principle. Black holes that are feeding way too fast are going to be producing so much brightness and releasing so much energy, which is of course produced by their accretion disk, that all of this light will become so bright and so intense that it's actually going to start pushing on everything around it, creating significant photon pressure. This is referred to as the Eddington limit in relation to the concept of Eddington luminosity. And so once radiation pressure is much higher than the pull from the gravity, the object technically should no longer be able to grow anymore.
But here's the puzzle. The Eddington limit should cap growth, yet this beast has blown past it. Either our models need refining, or these giants found loopholes in cosmic physics. Reminds me of how quasars once defied expectations in the 1960s.
And so, if a tiny black hole starts to grow at this limit for 13.8 billion years, its maximum size should be about 15 billion solar masses, based on these predictions. And while this newly discovered black hole is just a little bit smaller, 36.3, which of course makes this an ultramassive black hole, and one that's nearly at its limit. And it's also kind of interesting how this was discovered. As I mentioned, this was discovered inside the famous cosmic horseshoe, the object that only appears this way because of Einsteinian principles. This is of course the perfect example of what's known as the gravitational lens. And here we have two components, the central blob and the horseshoe shape or the smear around it. And it's really this central blob that's creating the lens. This is a very massive galaxy that produces a lot of gravitational distortions, basically bending the light behind it. Here's roughly how this effect is produced if we look at this from the side. And while in this particular case, this astonishing black hole was not discovered in a distant magnified source, but within the foreground blob, within this very massive galaxy acting as a gravitational lens itself.
Fascinating. Using a gravitational lens to reveal a hidden colossus in the lensing galaxy itself. It's almost poetic. Gravity's distortion not only magnifies distant objects, but betrays the secrets of its own host.
Which by itself is already pretty unusual. And this black hole is technically considered to be dormant, or in other words, it's not actively producing energy and not actively accreting material, with this detection relying purely on immense gravitational pull, with the effects then observed in the surrounding features. But to discover this black hole and to find its mass, researchers had to rely on at least two separate techniques, strong gravitational lensing being one, and stellar dynamics being the second. And so in a typical gravitationally lensed system, the extent to which light is bent directly reveals the strength of the gravitational field, which is usually linked to the mass of the foreground object. And generally, masses of supermassive black holes are somewhat proportional to the masses of their host galaxies, and that of course allows us to indirectly calculate the central black hole's mass. Something very similar was done for the two record holders, the galaxy we discussed previously known as Phoenix A, and the biggest and the most massive galaxy in the entire universe, IC 1101. Both of them are believed to contain two of the largest ultramassive black holes in existence. But this indirect calculation is obviously not very robust and only gives us an approximation. And so the key to this discovery was the presence of the radial arc near the center of the lens, which appeared to be extremely sensitive to the inner mass structure of the entire galaxy. And that allowed the researchers to recalculate the overall mass in the center of the galaxy, specifically focusing on the dark matter distribution and the overall distribution of the central galactic mass. And this was then reinforced by the model focusing on the star motion in the entire galaxy.
On second thought, the precision here is truly impressive. Star motions as cosmic yardsticks. It echoes how Andrea Gheze's team clinched Sagittarius A's existence. Observational ingenuity never ceases to amaze me.
And so then, by using the Hubble Space Telescope images that revealed this radial arc with a lot of detail, they were able to determine the total mass of matter and the overall velocity of stars moving around the central point. And the motion of stars in the center is of course how the central black hole in the Milky Way was officially discovered and confirmed as well. This, by the way, eventually led to the Nobel Prize. And so here, by using the multi-unit spectroscopic explorer, with several observations going back to 2007, researchers confirmed the overall motion of stars, measuring their mean velocity and velocity dispersion. And here the velocity was about 366 km per second. And by then comparing this with models of dark matter distribution, and by modeling the black hole itself, researchers were able to confirm the mass of the central point, or the central black hole, relatively accurately, confirming the mass at 36.3 billion solar masses with approximately 5 sigma detection, which in science of course means that it's almost certainly correct. And by itself, this discovery does have a lot of different implications. Now first, while there have been detections of much more massive black holes, for example the famous TON 618 we've discussed a few years back,
Right then, 5 sigma leaves little room for doubt. This isn't some speculative mass estimate. Compared with TON 618's slippery numbers, this feels far more concrete, a genuine benchmark for ultramassive black holes.
A black hole whose mass was initially estimated to be 66 billion solar masses. Since this was done using very different techniques and usually a lot of assumptions, in many cases the masses of these black holes had to be recalculated and usually downgraded. So for example today, it's actually believed that this is maybe about 40 billion solar masses, or even less. Yet here the certainty is much higher, mostly because of the advanced methodology. But this is also important because of the galaxy where this is located. This is technically a fossil galaxy, meaning that this is a single massive galaxy believed to have been created from a merger of an entire galactic cluster over cosmic time. So billions of years ago, this was probably at least a dozen galaxies, which eventually combined into a single object. And in this scenario, the individual supermassive black holes, located at the centers of those merging galaxies, would eventually coalesce into a single ultramassive black hole that seems to be observed inside of this cosmic horseshoe. And this provides us with a very important clue. The clue in regards to how these black holes can become so ridiculously massive, even though the universe is just not old enough yet.
Imagine that, an entire cluster collapsing into one fossil galaxy, its black holes merging like seeds in a cosmic pomegranate. Yet even in that scenario, this Leviathan is bigger than statistics predict. That's where mysteries begin.
And so here, an astrophysicist, Thomas Collette, believes that what we're seeing here is the end state of galactic formation and the finale for what happens to most black holes in various galactic clusters. But even for this galaxy, this particular black hole might be just a little bit too massive. As a matter of fact, here, it was discovered to be approximately 1.5 standard deviations above the mean, suggesting that sometimes these overly massive black holes somehow end up being present inside a lot of BCGs, brightest cluster galaxies. Galaxies that are usually the most massive and the brightest galaxies in the entire cluster, and that for some reason also contain the most massive black hole as well. For example, there's a BCG right there, and it just so happens that it also contains a much more massive black hole compared to its neighbors, implying that some of these galaxies and these galactic systems seem to have a distinct evolutionary pathway compared to everything around them. But here the explanation might be a little bit counterintuitive. This might be the result of what's known as black hole scouring, or specifically binary supermassive black hole scouring, where merging black holes dynamically expel a lot of stars from the system.
My goodness, the idea of scouring, black holes ejecting stars wholesale, is both violent and elegant. If true, these giants reshape their galaxies not just by gravity, but by sheer dynamical cleansing,
reducing the number of stars in the entire galaxy, and thus making black holes represent a much higher mass in the whole system. At the same time, a lot of these black holes very likely become extremely active, and in this case, the feedback from this black hole activity can also prevent star formation as well. Or alternatively, maybe these were created by some other means, and are maybe connected to some other mysteries discovered by the James Webb. For example, the now famous little red dots. You can learn about this phenomenon in one of the videos in the description. But when it comes to this research, here the combination of gravitational lensing with stellar dynamics definitely played a very important role in discovering the almost exact mass of this black hole, suggesting that something very similar could be done in the future for a lot of other targets, including the previously mentioned Phoenix A and potentially TON 618. But right now this still doesn't provide us with the explanation why some of these ultramassive black holes seem to be still above the potential theoretical limit. As a matter of fact, right now there are at least 3, with the one right here that we discussed approximately 5 years ago.
That's quite a bold claim. Spin as the secret sauce. We've long known rotation matters in accretion physics, but scaling it to tens of billions of solar masses stretches imagination. Still, physics often surprises.
Basically being above that 50 billion solar masses limit that right now is kind of difficult to explain. There's actually maybe just one explanation, the explanation being that these black holes are also spinning very fast and are thus able to consume mass much more efficiently, but for now at least this is all just a speculation, and these 3 galaxies with these 3 ultramassive black holes remain a bit of a mystery. But much more importantly, future missions such as the Euclid mission are expected to discover hundreds of thousands of gravitational lenses. And so by combining this with the extremely large telescope observations, which can help us study star motion, it will become possible to work out exact masses for many of these ultramassive black holes in the near future. And that means that we're going to be definitely discussing more of these discoveries in possibly the next few months, and very likely discuss more ultramassive black holes, and of course mysteries of their formation, because right now this is one of the bigger astrophysical mysteries.
Stepping back, one appreciates how this fits into the broader cosmic puzzle. Euclid and ELT may well revolutionize our census of black holes. Each discovery forces us to rewrite the universe's growth diary, page by page.
The mysteries that still does not have a very good resolution, mostly because we just don't understand how these black holes can get so massive so quick. And so until future discoveries, that's pretty much all I wanted to mention. Thank you for watching, subscribe, come back tomorrow to learn something else, stay wonderful, I'll see you tomorrow, and as always, bye bye.